Yes, thank you. All right, so I have to stand here. Well, welcome all to Pygrunn 2024. Thank you for choosing my talk in this morning. I was introduced already, but who am I? Well, my name is Vito Minheere. And for the people in the back, well, it's not a very big room, but this is what I look like. And if you want to talk to me, I'm wearing the same sweater right now, so the brown one. Yeah, that's very important. And of course, the motorcycles. So this is a picture of me on my motorcycle on the track of Asse nearby. I thought, yeah, I'll throw that in. So what am I going to talk about? That's the important part, right? It was something about simplifying and efficiency, and I think I put something about COBOL in there as well. It was also in the first slide, but ChatGPT wrote it wrong. Yeah, so I did a project with COBOL and Python, so I'm going to explain it a little bit to you. The details don't really matter that much, but you need to get a grasp of it. Then the first version I wrote of the replaced COBOL program with my own Python. Then encountering real-world data. Well, I guess most people know what will happen next. Optimizing it afterwards to get it working. And then the lessons I learned along the way, and hopefully I can share it with you. So the project itself, it was a government agency, so of course COBOL is there. It was, for the people who don't know, COBOL is a very quick introduction. It's the Common Business-Oriented Language. It's a language from the 1960s made by Grace Hopper. I think it was even for the military at that time. Yeah, it's a very basic language. There's no dynamic structures at all, not even loops. Very, very basic data types. And it runs on mainframes. So they had a mainframe at the agency I was at. I didn't see it because they didn't want to show it to me, but they did have a lot of COBOL code left over. So they gave me, they showed it to me, and it was 1,500 lines of COBOL, was the first script I opened. I was, oh God, what am I doing? So I did some more Python projects there, and I made them a lot faster, and they were happy about it. And they said, hey, we have this issue with our old COBOL program. We want to get rid of the server because the license is very expensive, and we are migrating it. But in the meantime, can't you just speed it up in Python, because it's not, the ETL script it was running wasn't that hard. Well, you can see on the picture, there's a data division. So that was the largest part of the file, was just explaining what the data was as an input and what output they get. Well, in Python, you could do this dynamically, so you could scrap all that. So that got rid of a lot of lines from the 1,500. And then we have the whole procedure part over there. That explains what all the things will do in the code. Well, it's very verbose. And when I looked at it, it was, well, the input and output defined. It was all generated code. So they used the code generator to generate their COBOL script. So instead of writing loops, if they were even possible in COBOL, they just copied the same 50 lines of code 30 times. So I looked at it and said, why did you do this? Yeah, we used the generator, so it didn't matter anymore. I said, yeah, but if someone opens the program like I did, and they see 1,500 lines, they get scared and close it, and they will never try to make it better. I said, when we do Python, we can just fix it. And then they also had multiple files, which almost did the same thing with repeated code. So there was a lot of code there, but the actual logic in it was a bit smaller. Lucky for me. And it was a monthly ETL pipeline, so it didn't have to be that fast. So hey, Python would probably be good enough. Well, the first thing I encountered was the file format. It's a colorful picture, so hopefully it works. This isn't the data, this is different data. The bubonic plague was not something I was working with. But this is the file format I have. It's called the fixed width format. So instead of having columns and all those things defined, it was just, oh, you have the first column, that's a length of 6, so you get 6 characters. Then you get a space or non-printable. In my case, it was non-printable characters, because spaces were valid characters as well. And as you can see, the name of the bubonic plague, it has a length of 40. So it's always the same length, and it's filled with spaces in this case. So it's annoying to load it. In Python, I just threw it in a dictionary. So that was the dynamic part. But yeah, it gets really annoying to have to add stuff, get rid of things. If you delete one character, you have to add a space to get it into the same length. So I wrote the first version of it, and the program in itself was a basic transformation. The data came in, it was a bunch of records. We had a lot of, I was working with the senior who wrote the program a long time ago, and he had some test samples for me. All the edge cases were there, so we had a bunch of files I could run through, and they were all working fine. And what I did was, it looked at a code in the strings, and mapped that code to a dictionary, and then that was mapped to a function which would transform that row and then write it somewhere else. Well, the first version, everything was in memory because that worked for my tests and my edge cases. No issues there. It had lots of error handling because everything was very important at that time, and the other databases it encountered, they could not handle if something was wrong. There was a lot of parsing of data because every row had a date or a date time. I will come back to that later. So every row needed to have a date parsed, which was very intensive. And I tested all the edge cases, covered every base, even stuff that wasn't in the edge cases or in the test itself, because there was no documentation in the code. And I had to run into issues, and then the senior would say, oh yeah, that didn't work. And then he would have to make some solution, and I would have to implement it. So yeah, real world data came, and as you can see in the picture, it was bigger than my 10 edge case files with 100 rows in it. They forgot to mention that in the end, the actual data was billions of rows. And I put it all in memory. So it crashed immediately. So I said, yeah, it's all done. I worked on it for a couple of weeks. I said, yeah, we can run it. And it crashed. Like, oh, great. So I got it working in the end with my very naive solution. And it took 18 days. They're like, oh, okay, it's a monthly run, so maybe that would work. And then they said, yeah, but the previous COBOL implementation took only 50 hours. It's like, oh, that's not good. Well, all the trust in Python was lost. So they weren't very happy with it anymore. But I said, okay, let me see if I can do some optimization, because you forgot to mention it was billions of rows in one data set. So I should have done that different. So my reaction at first, why is it so slow? I mean, it's Python. I can run a couple of million lines in pandas or other code, and it's fine. Why was it crashing? What is it even doing all the time? What is taking 18 days? And then, what are the bottlenecks? That's the actual question you want to ask. So then the thing was, how do I find the bottlenecks? Well, what I used for that was profilers. So a profiler is also a piece of code that can analyze your code and then say things about that. So execution time, memory usage, how many times functions are called. And I was using two profilers to really get into depth with it. I had cProfile and line profiler. Well, cProfile on the left, it's a deterministic one, so it talks about your whole program at once. It's built into the Python library, so that was very useful. I didn't have to install extra stuff. And the other people working there could also work with it without having to set up the virtual environments and all that things, because that was a bit too much for them at the start. It measures per function, so it can tell you which functions were called and how many times, also in the Python library itself. So it's very nice. And it looks into time consumption. So you can say, okay, how long does my entire program take, and how much of the time is spent in these functions? Well, that's nice, but what if one function is the bottleneck? Then I would look at the line profiler. Then you can profile your function, a single function, line by line. It is an external package, so I had to install it. You can see the measures of what cProfile had, so how many times it's called, how long it takes, but then per line of code instead of per function. And this is how you get to the performance bottlenecks. So this is a screenshot of some code. I wrote a small file to generate Fibonacci numbers, I guess in this case. Oh no, my bad, it's the datetime. So I mentioned the dates and datetimes at the start. I was focusing on that part because that was the part that was running most time. And it was because every record had a datetime that needed to be parsed. So and that was the reason. Well, you can see in the profile that it is running a random in the beginning. And the total time for that is 3.6 seconds for the entire program. And we see that it has almost the most amount of calls. We say that the second row has even more calls than that, so double of it. But this also adds in the built-in methods of Python, indexing, because it's doing something with a list. Again, that's nice, but that's not my code. I want to see my own code. So I had to look into the kernprof line profiler. So this does check only the part datetime function of my code. And I made a test set of around 1 million lines, I guess. Yeah, that seems good. And I ran through it. And this is the kind of code I used in the actual COBOL to Python program. So we were slicing the strings. I first did it with checking the datetimes, then stripping them, setting it to a datetime object. But if you did that millions of times or billions of times, it was very slow. And in the end, we decided, okay, the data in the database, we're going to say that it is correct most of the time. So we can easily parse the dates. And because it was the fixed width data format, we could also say, okay, we can also always assume that this data exists if you slice it, because it's always the same width. So that was very handy. I could get rid of some of the slower exception handling there. But you can see that all of the lines are being run 1 million times because it needs to check every part. But we had dates and datetimes in there, and a date doesn't have any hour, minute, or seconds, or even microseconds. So that's a huge waste to look into it. Oh. Yes, so the optimizations I did, I did a bunch of them. So if you want to learn more about it, you can always talk to me after this presentation, but I had to stick it to a quicker schedule. While returning results early, so as we can see in the previous example, from a date to a datetime, that could be done way faster. And caching results of the functions. A PowerPoint put the car there. I have no idea why, but it made it faster. So the car is faster than walking. Right, the early returns. So as I said earlier, we have a date and a datetime, and it was in this format. So this was the format. They added a plus because that was what COBOL wanted, and then it's the same length. And we had a datetime. So the fields are both the same length, but the first one has spaces added. We could have said, okay, if we find spaces at the end, it could be a date. But it was all text fields, so they could put within whatever they wanted in there, so that could fail. Well, this first format will parse to this one, and the second one will be parsed to this one, and we needed to add some zeros. And to the first one, we needed to add a lot of spaces, which you don't see. So we go back to the line profiler, and we take a look again. And now I have, again, the 1 million. So I made a test set of about 700,000 datetimes and 300,000 dates. And I mixed them, and we can see that every line of this will take, it gets executed 1 million times. But what if we return early and we skip the entire part for the minutes and the seconds? So we check if there's an hour, we slice it, then it's a empty string or just spaces, which is also an empty string, which is then false in Python. And then you can say, well, if there's no hour, then just return the dates we already parsed. And as you can see, that will move it from the 1 million to about 700,000. And if we go back, the total time here was 4.4 seconds, and now it's 3.4 seconds. So you can say, it's about 20% faster. Maybe not so impressive for the 1 second, but remember the 18 days? That was now 15 days. So almost 2 weeks, so we could almost run it twice in a month. Yeah, I had to be a bit optimistic, right? Say, I'm getting there. I just scraped off 4 days. I can get 4 days more. So then the next step was caching. Because, as we can see, the So we had 30 years of data. I had to parse every time, every month, because they were encrypting it in a different way for security, and they wanted to run the whole data set. Well, 30 years times 365 days is about 10,950 different days, give or take a few because of leap years. Well, it's only 10,900 different ones, but we have 1 billion plus records, so there are a lot of duplicates. And parsing is slow, but a lookup for a duplicate is very, very fast. So we have the same function parameters, we have the same date that comes in multiple times, and it will always return the same result, because we just parse the date. So what will be a solution for that? We can use caching, which is always already in the Python library. So that was very simple to implement. It was just one line, but what it does under the hood is we have the LRU cache. So we go to parse date, and we call the function. Then the function checks the cache first, which is empty. Then it will call the function parse date. It will return the date you saw before. Then it will write that to the cache as a kind of dictionary, a lookup. So the left part is the parameter we get into, and the right part is then the output we get. And then if we hit it again with the same input, it will just check the cache, see that it already exists, and then returns it. Well, this would speed it up significantly again. So here I have the same part of the code with the early return from before. And now it takes about 5.6 seconds. And if I cache it, it was about 3.6 seconds. And as you can see, I changed nothing in the code. We have the add profile at the start, and we have the add LRU cache again added to it. That was the only thing I needed to do to cache this result. I tried caching multiple functions, but that didn't work that good. It only worked for the dates in my experience. But yeah, that saved again about 20%. So a lot more days there. So a lot more days there. How am I in time? Very good. Yeah, too fast. So I had some lessons that I learned. I had some other optimizations as well, but I didn't know if I could make it in time. But yeah, I already optimized my whole talk, so this was again very, very fast. You can ask questions about the other ones, and I can explain them. But lessons learned. Well, always benchmark first. They didn't want to tell me how long their program would run, because, then it would be like a guess, and you would just try and we'll see how far you could get. Yeah, they just, when I said, it will take 18 days, we extrapolated it from a test set of maybe 100,000 records, because that didn't crash. That was the smaller file. And then they said, okay, if it takes this amount of time, then for the 2 billion records, it will take this amount of time. And that's way too long. But if I benchmarked it first, if I knew how long the COBOL code would take, then I had a better idea what I was going to do. And then the second, know what your target is. So if people want something optimized, or they want it faster or made better, how much better, how much faster are we talking about? Even though it's a monthly script, maybe something fails and then we'll run it again. Well, if it takes 18 days and it fails on the 17th day, you're not going to make it in that month. So then other parts of the whole system would also be delayed by that amount of time. But yeah, they were very open about, just make it faster and we'll see. Yeah, we just had to set a target, and then we could have gone. It's better to have a target and focus on that. And then you can explain, we have to make these changes, we have to make these sacrifices, getting rid of some error handling, and then assuming that databases will handle it, so that we can get that target. Well, another one is to get profilers and line profilers. And maybe people were already using it. I was using the C profiler a lot, but not a line profiler to really get into depth about how much times something is called in your line. And then you can see that, why is it being called 1 million times? One thing I really ran into was using the get method on a dictionary. So that's always the safe one. So you don't have to do error handling if it fails, because it will return none, and you can do something about that. But the issue was, if you have your billion records, and 99% of them do exist, you're doing the lookup and the error handling part of it around 900 billion times, which you didn't need to do at all. So then I got rid of that. So that saved me a lot of the executions. And then I just handled the really small part of edge cases with my own exception handling, which was faster. Even though you would say, oh, the get method is a better one to use instead of just naively getting it. And refactor your logic to return early. That was a huge savings. A huge savings I had. I had other parts of functions that would do different things. But if you then reverse the logic, you could get out at the first moment. Oh, this part happens, then you do this, and then return it, instead of going through the whole list of all the changes that could be done and returning it early. Also with a lot of checks about the length. Oh, if it's too long, the line is bad, throw it away. Instead of trying to go through all the steps and then at the end say, oh, the line is bad, get rid of it. Well, that was my very short talk about it. Thank you for listening.